Example 5, the following 7 Scrabble tiles remain in a bag. How many 4-letter words can be made from the 7 letters? So when they say a word, they're not really saying like real words. It's like just 4 letters. So W-Y-O-M would count as a word, even if it's not actually a word. So how many ways to do that? So basically what we're doing is picking 4 of these letters out of the 7. And order matters. So this is just a permutation. 7p4. 7p4. $8.40. Again, it's a permutation because the order matters. Part B, 4 tiles are drawn from the bag, one after another without replacement. That's a pretty important phrase right there, without replacement. What is the probability that the letters W, I, N, G are drawn in that order? So W, I, N, G. It has to be a W, and then an I, and then an N, and then a G. There's only one way to do that. Probability, remember, is part over total. So there's one way out of the total number of ways. Well, we just found the total number of ways was 7p4, or 1 over 840. And if you change that to a decimal, 1 out of 840, 0.00119, about. Part C, 4 tiles are drawn from the bag, one after another without replacement. What is the probability that the letters W, I, N, G are drawn in any order? So this is a different question, okay? Or they're drawing them in any order. So it's probability, so it's part over total, and the total is still going to be the exact same thing. We're taking those 7 letters and pulling out 4 in any order. That would be the total number of ways. But what we're trying to do is have these 4 letters spell some word, but it says in any order. So in W, G, I, that would be a different word. Okay, that would be a different word. So basically what we're trying to do is shuffle those 4 letters, I guess. And so you could think of it as a blanks problem if you want. There'd be 4 letters to pick first, and then 3, and then 2, and then 1. Or you could think of that as a factorial if you want. That's 4 factorial. Or you could think of it as there are 4 letters, and I'm going to order all 4 of them. Any way you want to think about it, that's 24 over 840. And that's going to be roughly 0.0286. Part D, 4 tiles are drawn from the bag, one after another with replacement. Notice how this changes the problem. What is the probability that the letters W, I, N, G are drawn in that order? Okay, so this time the denominator is going to be different because it's not going to be 7p4 because 7p4 says 7 times 6 times 5 times 4. And we pull one out and then we've only got 6 left. And then we pull one out and then we've only got 5 left. And we pull one out and we've only got 4 left. So with replacement, we pull one out and we still have 7 left because we put that thing back. We replaced it. And then we replaced it. And then we've still got 7 to choose from and 7 to choose from. So this time there's only one way of pulling out wing, but you've got 7 to the 4th power number of possible ways of doing that. 7 to the 4th power. It's 2401. So 1 over 2401. If you want to leave it as a fraction, that's fine. Or decimal, 3 zeros and a 416, probably be good. Either way. Number 6, find the probability that at least 2 of 28 people in a room have the same birthday. This is a very famous problem called the birthday problem. And it seems really complicated. And it's kind of just a strange problem, I suppose. So if you think about what it means when it says at least 2 people, have the same birthday, it means that either 2 people have the same, or 3 people have the same, or 4 people have the same, or 5 people have the same, or 6 people, or 7, or all the way up to all 28 people have the same birthday. Now, you realize that's not very likely, but what ends up happening is when you add up all of those different cases, the probability is a lot higher than what you would think. So what we're going to utilize here is the complement rule that says the probability of B happening, let's call that birthday, equals 1 minus the probability of not birthday. So anyway, what we're going to do for this birthday problem is, instead of adding all of these things up, which is going to take forever, we're going to say the only other case that could happen is nobody has the same. Okay, you wouldn't say 1, you'd say, because one person having the same birthday doesn't make sense. So either nobody has the same birthday, or 2 people could match, or 3 people, or 4 people. So basically what we're going to do is only going to look at if everybody has a different birthday. We'll say 1 minus that, and that will be it. So we're going to do 1 minus the probability that everybody has a different birthday. And so how that's going to work is, we've got 28 people and each of them have a different birthday. So we're going to have the assumption that a year has 365 days in it. And we're going to select 28 different days of those 365. So I wrote that. That looks like a probability. Let's change this to where it looks like a permutation. Okay. 365 P28. That's a permutation, not probability. Okay. That means we've got 365 days, and we're going to pick 28 of them in order, because the order matters, because, you know, if you and I have 2 different birthdays and we switch them, that would be completely different. Now, the denominator of that is, okay, if you think about it as a blanks problem, there would be 365 days to choose from for the first person, and then 365 days for the second person, and 365 for the third person. Okay. I guess we could totally think of it like a blanks problem and say there are, let's see, 365 days, and then after you choose one, there'd be 364 days for the next person, and 363 days for the next person, and so on and so on. So that's where this permutation comes from. Let's get rid of all that. I need that room. But anyway, it's out of 365 every single time. So that's kind of the formula. That's the formula, and we're gonna plug that into a calculator. We're gonna calculate that. All right. So the probability that at least 2 people out of 28 that have the same birthday. So let's see if this thing can handle it. 1 minus. I know some calculators won't handle numbers this big, because it is a pretty big number. Okay, 0.6545. That seems shockingly high, doesn't it? That means if you're in a room with 28 people, there is a 65% chance that 2 or more people will have the same birthday. I think that's surprisingly high. 65% chance that 2 or more people have the same birthday out of 28. So, you know, what if there were 50 people? If there were 50 people, you would do 1 minus 365 P50 over 365 to the 50th power. So, you know, whatever that is, I bet that's really, really high too. Let's see if it'll work. oops, not answer, 1 minus. What do we do, 50 people? Check it out. With 50 people in a room, there's a 97% chance that two or more people will match. That's really, really high. You would think it would be a lot lower, but with 50 people, that's what you'd get, about 0.97. What was it? 04. All right, let's move on. Last one. 5 apples, 6 bananas, and 7 lemons are sitting on a table. How many ways are there to line up the fruit in a row? So we've done this problem before. You've got 5 apples and 6 bananas and 7 lemons. How many ways to line up the fruit? How many ways of shuffling the fruit? So this is the same thing as the Mississippi question. They're indistinguishable, and we're going to figure out how to shuffle the letters or the fruits. Okay, so how many different ways? There are 18 letters. There are 18 fruits. And if they were all different, the answer would just be 18 factorial. But we're going to divide off the number of ways of shuffling the apples and the number of ways of shuffling the bananas and the number of ways of shuffling the lemons. So once you type that in, and again, we've done this before, we get 14,702,688. Don't forget to use your parentheses. If you've got a TI calculator, you must put parentheses right there, or it's not going to give you the right answer. Be very careful. Part B. Find the probability that all fruit of the same kind are placed together. So notice it's a probability question, so it's going to be part over total. And this one seems confusing because you're like, well, they are all together. There's the apples and the bananas and the lemons, but that's not exactly what we're doing, okay? This answer, they could all be shuffled up, and you don't know really what order they're in. So when they say all of the fruit of the same kind are placed together, if you think about it, what I've got listed are all the apples, then all the bananas, and all the lemons. But it could be apples, lemons, bananas, or we could have started with bananas, apples, lemons, or bananas, lemons, apples. Could have started with the lemons and gone apples, bananas, or lemons, banana, apple. That's really it. That's how they would have to be arranged. Those six ways are the only ways that you could put all the fruits together. So that's the numerator when we talk about probability. Probability is part over total. We're going to have 6 because there's 6 different ways of shuffling the different types of fruits over 14,702,688. And if you do that, if you plug that in on your calculator, you're going to get a lot of zeros there. 6 zeros. 408. Okay. Now, another way of thinking about this, you can think about it as a blanks problem. There are 3 ways of picking the first fruit, and then 2 ways, and then 1 way. So it might be healthy if you can think about it as a factorial. That's 3 factorial. That way, if there were 4 different fruits, you could say it was 4 factorial or so on or so on. But anyway, 6 ways of shuffling the fruits out of that 14 million number. There's your probability.